Welcome to the presentation of our CVPR paper, DeepLSD, Line Segment Detection and Refinement with Deep Image Gradients. DeepLSD is a novel line segment detector that combines the robustness of deep learning through a novel attraction field representation, which require no human labeling. And it still enjoys the accuracy brought by low-level strategies thanks to their pixel-accurate methods. Finally, DeepLSD can refine existing lines or its own lines through an optimization that can further boost the accuracy and repeatability of the lines. Here's a demo of DeepLSD in action, where you can see in the top right the distance field and in the bottom left the angle field predicted by our network, and in the bottom right the resulting line segments. These lines are highly accurate and robust to image conditions such as lighting variations. So why do we need DeepLSD? First, initially, handcrafted line segment detectors, such as LSD, were very fast. They were also very well localized, meaning that they usually have only an error in the image to the actual line localization of at most a pixel. However, they were not robust to image changes, such as lighting variations or here in this image, the fog. On the other hand, we have the learned line detections. They can be made robust to these image changes by being trained on these different image conditions. They can also target specific lines, such as wireframes. However, they are usually poorly localized, meaning they can have several pixel errors in their localization in the image, and they often require human labels for training. In contrast, DeepLSD is both robust to these image changes by being trained on different datasets and conditions. It is well localized in the image, and finally, it does not require any human label. So how does it work? First, we need a suitable line representation, and we adopt the attraction field one. We have two outputs in this representation, the first one being the line distance field, where every pixel in this image is voting for the closest line and returning the distance to that closest line. The second one is the line angle field, where every pixel is returning the orientation of that closest line. We thus obtain two continuous images, the line distance and the line angle fields, which are suitable to be learned with deep learning. However, we need a ground truth for this, and we use homography adaptation to obtain this ground truth. It starts with a single image, which is then warped with multiple homographies. And on each of these warped images, we apply an existing line segment detector, which can be anything, but we used LSD in our case. The lines are then warped back into the original frame and can be converted into our line distance and angle field. And finally, all these different representations are aggregated into a single one through a robust average. This is the ground truth that we used to supervise our network. The network is simple. It's a unit-like network, which takes a single image as input and outputs the distance and the angle field. Thus, we can train it on multiple datasets and conditions to obtain the required robustness. Next, let's see how to obtain line segments based on this attraction field representation. First, we convert our new representation into a deep image gradient. So the distance field is easily converted into the magnitude of the image gradient and the angle field into the orientation of the gradient. And based on this image gradient, we can apply any existing traditional detector, such as LSD, and then get the line segment. Since these methods are highly accurate, based on the pixel gradient, we can keep the same accuracy for our method. Finally, the lines can be also even more refined through an optimization. Given the existing lines and the predicted distance and angle field, we can solve an energy-based minimization so that the lines better fit the distance and the angle field. This brings additional accuracy and repeatability to the lines. Here's a simple experiment where we can see the benefits of our refinement. Here we compare 4 different line detectors and evaluate them on homography estimation on the wireframe dataset, returning the success rate in the y-axis. After refinement, all baseline significantly increased their score on homography estimation, except for DeepLSD, which is already highly accurate on this easy dataset. DeepLSD, thanks to its accuracy and robustness, can unlock novel applications, such as here, 3D line reconstruction. This reconstruction has been obtained with our other submission to CVPR, 3D line mapping revisited. And with just a few images, we are able to reconstruct with accuracy and completeness a full scene layout with all the line segments in it. These line maps can be also used for visual localization. Here in this slide, we present the results for a point-based visual localization, where we want to relocalize the given image into a known map. We drew in blue the lines and the points that can be observed in this image. And the red lines and green points are the features coming from the map that have been reprojected in this image based on the predicted camera pose by the pipeline. As you can see, the red and the blue lines are misaligned, meaning that the predicted camera pose is inaccurate. However, after integrating our lines into the pipeline, we obtain the following results. You can see now that the red lines are perfectly aligned with the blue ones, meaning that the predicted camera pose is perfectly accurate. Also, in terms of numbers, the pose estimation accuracy is increasing by 43% on these scenes coming from 7 scenes stairs, which is known to be very difficult for point-based methods because of low texture, whereas the lines can enjoy more structure and repeated patterns actually helps for the localization. So, in summary, DeepLSD is a hybrid line detector which combines the robustness of deep learning with the accuracy of handcrafted detectors, and it requires no human labels. Its line refinement can also be used on existing line detectors to further boost their accuracy. And finally, the new robustness and accuracy brought by DeepLSD can unlock novel line-based tasks, such as 3D reconstruction and visual localization, and can obtain state-of-the-art results on several benchmarks. In case you want to know more about our method, please check the following resources. Thank you for your attention.